Webb measured 129 galaxies per square arc minute to map something that cannot emit, absorb, reflect, or block light. But the blue web in NASA's image is not a photograph of dark matter. It is a reconstruction of gravity, built from tiny distortions hidden in the shapes of distant galaxies. That distinction is the entire story. The James Webb Space Telescope spent about 255 hours observing the cosmos field and identified nearly 800,000 galaxies, some too faint for earlier surveys to detect. The field covers an area of sky about 2.5 times larger than the full moon. From those galaxies, researchers produced a mass map with an angular resolution of about 1 arc minute, more than twice the resolution of earlier Hubble maps of the same region. What came into focus was not a smooth fog. Dense concentrations were joined by fainter bridges. Known galaxy clusters appeared as peaks. Lower density regions opened between them. Across one narrow window in the sky, the invisible structure beneath the visible universe became sharper than it had ever been before. To build that map, Webb did not search for dark matter particles. It watched background galaxies. Light normally travels along the straightest path available through spacetime. Mass changes that geometry. When light from a distant galaxy crosses a foreground concentration of matter, its path bends slightly before reaching Earth. A massive cluster can stretch one galaxy into an obvious arc. Weak gravitational lensing is subtler. Thousands of galaxies appear only a little more aligned or distorted than chance should allow. One galaxy is not enough. Its true shape is unknown. But average the shapes of hundreds of thousands of galaxies, account for Webb's optics, estimate their distances, and a coherent pattern emerges. Researchers can work backward from that pattern to reconstruct the projected mass along the line of sight. The word projected matters. This is a map of total mass between Webb and those background galaxies, compressed across cosmic distance. Ordinary matter contributes too. Astronomers compare the reconstruction with galaxy counts and X-ray observations to see where luminous matter and hot gas sit. Because ordinary matter represents only about 1/6 of all matter in the standard cosmological model, most of the gravitational structure is attributed to dark matter. The new map revealed roughly 10 times as many usable galaxies as ground-based maps of this field, and about twice as many as Hubble's. It also recovered finer substructures that the earlier reconstructions blurred together. That added source density turned weak distortions into a much more detailed map.
Diana Scognamiglio, the study's lead author at NASA's Jet Propulsion Laboratory, described the change as moving from a blurry picture to the invisible scaffolding of the universe in far greater detail. But here's the first problem. A sharper map can show where the extra gravity is concentrated without revealing what creates that gravity. We can trace the skeleton, we still cannot identify the material.
Dark matter does not simply surround finished galaxies like packaging. In the standard picture of cosmic history, it helped create the places where galaxies could form. After the early universe expanded and cooled, small variations in density grew under gravity. Dark matter began clumping before ordinary gas could efficiently cool into stars. Those concentrations pulled in hydrogen and helium. Galaxies grew inside dark matter halos. Groups and clusters assembled where filaments met. Over billions of years, a cosmic web emerged. Dense knots, narrow bridges, broad sheets, and underdense regions between them. The Webb reconstruction lets astronomers compare that picture with the real distribution of mass at much finer resolution. All 15 galaxy clusters in this field that were already known from X-ray observations appeared in the new weak lensing map above the study's detection threshold. The earlier Hubble reconstruction recovered only 8 of them. That is a powerful validation.
Hot gas seen in X-rays, concentrations of visible galaxies, and peaks in the gravitational reconstruction repeatedly occupied the same broad regions. The correspondence is what we expect if dark matter's gravity helped pull ordinary matter into the structures that later produced stars and planets. The map also shows extended low-amplitude bridges between some cluster-scale peaks. The authors describe these features carefully. They probably trace dark matter filaments too diffuse to shine strongly in X-rays or host obvious galaxy overdensities. The word probably is essential.
Weak lensing maps contain noise, and every feature must survive tests against instrumental and statistical effects. The team ran one of those tests by separating the lensing signal into two mathematical components. The component expected from real gravitational lensing was more than an order of magnitude stronger than the component used to diagnose residual systematics. That does not certify every blue contour as a physical filament. It does show that the overall map is not being dominated by a simple measurement artifact.
And then it gets stranger. The reconstruction contains mass peaks without clear counterparts in the available X-ray image or projected galaxy distribution. That does not mean Webb found isolated clumps made of pure dark matter.
It means the current visible inventory has not yet explained what gravity is showing. There are several possibilities. Separate structures may overlap along one line of sight. A counterpart may be too faint for another survey, and some peaks may weaken when future data arrive.
Yet those peaks matter precisely because they do not arrive with an obvious luminous label. They are places where gravity says there is structure, and the usual tracers do not immediately explain it. Follow-up observations can test whether they are distant clusters, superposed structures, diffuse matter, or noise. The question then becomes larger than one map. Does the Webb grow exactly as our standard model predicts at every scale? For now, the broad answer is compatible with the standard cold dark matter picture. The clusters, filaments, and underdensities resemble the structures produced by gravitational collapse in simulations. But compatibility is not identity, and one field cannot test the entire universe. The Cosmos map covers less than 1 square degree and compresses structures at different distances into a projected view.
Its strength is resolution, not completeness. It gives cosmologists a benchmark, a place where theories of structure formation must reproduce more detail than Hubble could resolve. It also exposes where the next observation should look. What it does not expose is the particle behind the pattern.
The most detailed feature in the Webb map and the deepest underground detector are asking different versions of the same question. The map measures dark matter through gravity. Particle experiments search for another interaction, a collision, a conversion, or an energy deposit that cannot be explained by known particles. So far, no candidate has been confirmed. Weakly interacting massive particles, or WIMPs, once dominated many experimental searches. Detectors containing tons of liquid xenon have become sensitive enough to exclude large regions of the simplest WIMP parameter space, yet they have reported no significant dark matter excess. Axions remain hypothetical. Sterile neutrinos, ultralight fields, dark photons, and primordial black holes each describe different possibilities, not a single agreed replacement. The Webb result does not rank those candidates. It does not show that dark matter is a heavy particle, a light wave, or a black hole population.
It does not even isolate dark matter from every atom on the map, pixel by pixel. It reconstructs projected total mass, then uses independent observations and the cosmic matter budget to interpret what dominates that mass. That limit prevents a dramatic but false conclusion. A beautiful blue filament is not a microscope image of unknown particles. It is evidence that an unseen gravitational component is arranged in structure. Still, structure can eventually eliminate possibilities. Different dark matter models predict different amounts of small-scale clumping, different halo shapes, and different rates at which structure forms. A map sharp enough to distinguish substructures gives researchers more locations and more scales on which to compare those predictions. The 2026 study calls its result a benchmark for testing theories about dark matter's nature, not a verdict on which theory won. And that's where the future surveys divide the job. Webb offers exceptional spatial resolution across a small field.
NASA's Roman Space Telescope is designed to map dark matter over an area roughly 4,400 times larger than the cosmos region, although it will not match Webb's detail. ESA's Euclid mission is measuring galaxy shapes and distances across a vast fraction of the extragalactic sky. Rubin Observatory began repeatedly imaging the southern sky in June 2026, building another enormous record of how visible structures are distributed. Together, wide surveys can reveal whether the patterns in cosmos are typical.
Webb can examine selected fields in greater detail. X-ray and spectroscopic observatories can determine which mass peaks contain hot gas or galaxies at the same distance. Particle detectors can keep testing whether dark matter interacts through anything other than gravity. None of those instruments alone closes the case. That is what makes the map important. It links the unknown particle to the history of galaxies without pretending those are the same problem. We began with a blue web that looks like a photograph.
It is not. Every strand was inferred from light bending by an amount too small to notice in any single galaxy. The reconstruction is indirect, projected, and limited to one patch of sky. And yet it recovered every known X-ray cluster in that field. It resolved structures Hubble blurred together. It exposed probable bridges between clusters and highlighted mass peaks that still need an explanation. We have not seen dark matter. We have seen what the universe does around it. That may be more unsettling. The substance remains unidentified, while its architecture is written across nearly every galaxy in the sky.